Hello and welcome to Circuit Math with Capella. I am here to help. First off, the basics. V equals I times R. Simple enough. V stands for voltage, which is measured in volts. It is the force at which the current is pushed through the wire, so how strong the battery is. I stands for current, measured in amperes, or amps. It's the amount of electrons in a wire. How much stuff is there for the battery to push forward? R stands for resistance. We measure it in ohms, which are represented by the omega symbol. Resistance is how much energy is taken out of the circuit by resistors, so how much is the battery's initial push slowed down along the course of the wire. In a series circuit, all resistors are on the same single path. The electrons are progressively slowed down by each resistor they encounter. This means the current is the same all around, but the total resistance is added up at each resistor, and the total voltage is used up partially by each resistor. These equations are used to represent these properties when calculating voltage, resistance, and current in a series circuit. Here we can see a single light bulb in a circuit. Note how bright it is since it gets all the voltage to itself. The press switch is simply to save power. The circuit is only connected when that switch is being pressed down. In the diagram for this circuit, the light bulb is represented as a jagged line, as all resistors are. The battery is a few parallel lines perpendicular to the wire, and the wires themselves are just simple lines. Secondly, I'm building a small series circuit with two light bulbs. Note how much dimmer they are, because they now each only have half the original voltage. They get equal amounts of voltage because they have the same resistance, because they're the exact same kind of light bulb. If we measured this circuit's current, we would find that it has a few less amps, since there's more overall resistance. In the diagram for this circuit, there are two resistors, so we'll see two jagged lines for our light bulbs. The battery is represented with that same set of perpendicular lines. The end with the longer line is the positive terminal, and the shorter line is the battery's negative terminal. On the other hand, we have parallel circuits, which are a different way of structuring resistors. Each resistor is on a separate wire path. Therefore, electrons are split between the wires as they go down. So current gets broken up, but voltage is equal all around because the electrons are pushed down each path with equal force. The total or equivalent resistance has a strange way of being calculated. In general, there's actually less overall resistance in a parallel circuit than there is in even one single resistor. But how is the total resistance less than the sum of its parts? Imagine that the current of electrons is a large group of people. They're all standing along the wire up top, waiting in line to go see the movies at the other battery terminal. The resistors are the ticket booths, which only a few people can pass through at a time. If you had just one ticket booth or resistor, these people are slowed down as they go through the line. If you have two resistors in series, it's like every person has to go through two ticket booths. But if you have two resistors or ticket booths in parallel, people get to split up and can move even faster down the line. So even though there are more resistors, we end up with more current moving faster overall. Now that we've got our equations and reasoning down, are you ready for some math? No? I'm sorry. First, let's go over a very simple series circuit. We know that adding the resistors in series will give us the total resistance, so that we can find that RT is 5 ohms. Using V equals I times R, we can also find IT. Following that, we can use V equals I times R twice more to find the voltage for each resistor, since we already know that current is the same all around. We can check our work using the voltage equation V1 plus V2 equals VT. Just to demonstrate how different the calculations can be, here's a circuit with all the same given numbers as the series circuit, but instead it's wired in parallel. Note how much lower the equivalent resistance is, and how the voltage and current are calculated in the opposite way. And of course, as always, feel free to ask the presenter, who is totally not me, if you have any questions about this math. But you probably already knew all that stuff, right? How about we finish up with a more complicated problem? Here we have a circuit where parallel and series patterns look like they're all over the place, so while you watch the math, I'll explain how it works. Since we have all the individual resistor values, our first task is to figure out the total resistance. We can do this by working from small to big. We have to find the combined resistance of the two resistors on a single branch of the parallel circuit, then use that total in calculating the resistance of the whole parallel segment. Finally, we combine that number with the other resistor in series. We have to treat each segment of this circuit like one resistor overall, then go back and calculate for the individual resistors. When we find the total current, we know that the current in series is equal all around. This means that the total current equals I1, and it also equals the total for the whole parallel segment. This is because the parallel segment is pretending to be a single resistor in series for this calculation. Once we find V1, we can subtract it from the total overall voltage to get the total voltage of just the parallel segment. Voltage is equal everywhere in the parallel part, so we can divide each parallel path resistor by this number to find the individual currents. Lastly, we divide out the voltage for the two resistors in series on the single parallel path. Anyway, thank you for watching. Let me know if you have any questions.